Hi, I am Dr. Juan Miguel Diaz, and I am presenting this work from my colleagues Dr. Delia Valles Rosales from New Mexico State University and Dr. Juan Francisco Hernandez Paz and Maestro en Ingeniería David Ataide Campus from University Autónoma de Ciudad Juárez. The work is Micromodeling Natural Fiber Composites Predicted Mechanical Properties of Reinforced Thermoplastics. Thermoplastics has been reinforced with different materials from long time ago. However, in the last 2 decades, several studies have been done to understand better this combination of fibers with thermoplastics. Some of the reinforcements that have been used are pine wood, cotton fiber, rapeseed, flax, sisal, among some fibers, and the most common thermoplastics has been polypropylene, polyethylene, vinyl, among others. Some studies have analyzed the shape and length of the fiber to improve mechanical properties. However, has not been very clear what is the best approach. In a study by Adhikari, he used pine wood dust with high-density polyethylene recycle to determine mechanical properties, and he had improved results of the tensile strength. Other works are working on other characteristics of long and short fiber. However, a work from Stark and Berger, they use pine wood flour with different sizes, and they obtain very good response on this combination. Mechanical properties are being basically determined by experimental methods. However, several micromechanical models have been used to do this. Many of these micromechanical models do not have a very good feed with experimental data. Most of them have linear response. And some of the studies used some micromechanical models from Rose, Ball, Hirsch, Halpensay, and others. The objective of this work is to do a experimental work of two materials, pecan wood and pine wood, doing a tensile test after fabrication, and do an analysis of predicting these materials using the micromechanical models. We use pine and pecan with 2 mesh sizes and 2 weight ratios. In materials and methods, we follow 3 basic approaches. The production of them was based, as mentioned, on 40 and 60 mesh with weight ratios 30 and 40%. The table 1 shows those combinations. Particle size was based on some of the studies that we have revised. Since it is not clear either a smaller size or bigger size will not affect the response, we will use this initial analysis of medium size and a small size particle. In the mill flour process, we use 1/16 inch for screening, the first step. The pine wood flour was from American Wood Company using 40 and 60 mesh. We use HDPE from ExxonMobil Company. The mill flour was finalized doing a sieve for the pecan wood flour using 40 and 60 mesh. Both flours were dried at 80 degrees centigrade for 24 hours. The last process was injection molding using a twin screw extruder for mixing and a injection molding machine with small piston using the setup mentioned. The materials property are in table 2. Mechanical testing for tensile strength was based on a universal tester machine, an Instron 5882. The standard used for tensile strength was ASTM D638-14. The predicting mechanical properties for tensile strength was based basically in 6 models. The first was a Boyle series, which basically has the tensile from fiber and matrix on a relation of volume fraction for each one. The parallel series model, the rails, also use similar approach. However, they are analyzing the relation when the fibers are in the stress direction. The Hirsch equation is a combination of both models. Also, we use the Halpin-Tsai equation, that is a adjusted model with a factor of adjustment. And then we have the Esten equation, which has a adjusted value for the volume fraction, and the FACA equation, which has a fiber shape and size correction factor. The results that we obtain for both materials were better than the metrics. We have that the HDP has 24.5 megapascals as ultimate tensile strength. Our table for 40mH shows that both materials have better response at 30 and 40%. In this next section, we analyze each mesh size. On figure 1, we are analyzing mesh 60 data. We can look that for pecan, we have values at 30% over predicted values, and at 40% we have under and over predicted. For pine, we see that have a similar behavior. We have it over and under predicted at 30 and 40%. However, we see that we have a better response of all values. For 40mH, the results shows that at 30 and 40% for pecan are all over the place. However, the Hirsch model is the one that best suiting for pecan as well for pine wood. That's very interesting for this particular model, because on the 60 mesh does not have this same behavior. So finally, we can say in these results that most of the micromechanical models are having a combination of either under predicting or over predicting the tensile response, which is a factor for not being able to fit better the experimental data. The model of FACA et al. Which is the only one that has correcting factor for fiber size and shape, is not really doing well for predicting values. And as we observe in table 3, most of the micromechanical models do not have a correction factor. Our conclusions are based on the following points. There is a lack of fit between test data and our predicted values from each of the micromechanical models. We see that the particle size factor in the bonding mechanism of the composite can be very important, and it's necessary to be understood better. We see that it's a paramount to analyze more in depth how particle size has effect on the response, since in this study we have a mixed results. The micromechanical models well developed, because we see a lot of fit data, so we need to see if a correction factor is needed. Thanks.